Bismillahirrahmanirrahim. Students, welcome back. Now I'll give you the second part of the lecture for week number 9, and we'll first discuss the concept of functions of two random variables. I have already given you some clue on what we mean by functions of two random variables, two discrete random variables in few of my previous lectures in the class. So today's first topic is functions of two random variables. Function of two random variables would mean we have a function of, say, two random variables x and y, and this is always another random variable. I have already told you when you apply any appropriate functional form on a random variable, whether one random variable or two random variables put together, you can generate another random variable. So now this w is a function. We intentionally are not using the notation f for the function because that is used for another particular purpose. We'll see that in chapter number 4. So now w is a function of two random variables x and y. So this is a new random variable, which means this should have some PMF, and there is a theorem that says that for a random variable w, which is defined through some functional form applied on random variables x and y, the PMF of w is nothing but the sum on all xy points for which, when you apply the functional form, it generates some value of w, and you sum it on all xy points. I am quite confident it is not clear as yet, but let me recall the example of throwing a four-sided fair die twice and then generate an example, and then we'll see how we can define a function of a random variable and how we can write the distribution of that random variable. So suppose you throw a fair four-sided die twice, and once you generate the value of a random variable x, and the second throw gives you the value of random variable y. So the possible values in this particular experiment can be 1, 2, 3, 4. You throw it first, you get a 1, or maybe you can get a 2 or 3 or 4, and similarly you throw it second time and you can get either a 4 or a 3 or a 2 or a 1. So we have 16 distribution points in this particular experiment. Give me a minute so that I could complete these the sample space. So these are the 16 points. Now suppose I define w as a minimum of x and y. So you see, now I am defining w as a random variable which is a function of two random variables x and y, but it is defined as a minimum of x and y points. So we'll utilize this sample space and then see how we can write the PMF of w. This should be easy for you now. You see, this point we have W is equal to 1. By the way, how many possibilities for W? It is defined as minimum of x and y, since x can go from 1 to 4 and y can go from 1 to 4. So W can go from 1 to 4 only. So what is the probability that W is equal to 1? How we can find this probability from this distribution or this sample space? You see here, x is equal to 1, y is equal to 1, so the minimum of these two is 1. Here x is equal to 2 but y is equal to 1, so the minimum of the 2 is 1 again here. So here W is equal to 1, here W is equal to 1, here also W is equal to 1 because it is 3 comma 1. So out of 3 and 1, 1 is the minimum, so W is equal to 1 here. Similarly, W is equal to 1 here, W is equal to 1 here, W is equal to 1 here, and W is equal to 1 here. So these 7 points where you have got W is equal to 1 here out of those 16 points. So the probability that W is equal to 1 is 7 by 16. Now what is the probability that W is equal to 2? Pick this point. It is 2 comma 1. It's not included as W is equal to 2. But take this particular point. Here x is equal to 2, y is equal to 2, so the minimum is equal to 2. Here the minimum is equal to 2, the minimum is equal to 2, the minimum is equal to 2, and the minimum is equal to 2. So these 5 points. So the probability that W is equal to 2 is 5 by 16. Similarly, the probability that W is equal to 3 is just 3 points. So 3 by 16 for W is equal to 3, and 1 by 16 for W is equal to 4, and obviously 0 otherwise. So you see, we have been able to write the PMF of a random variable W, which is a function of two variables x and y. X has a set of values from 1 to 4 and y has a set of values from 1 to 4, but W is obtained by applying the functional form, this particular functional form, on the giant occurrence. So these are the possibilities of all those giant occurrences, 16 possibilities. We see these 7 points for W is equal to 1, these 5 points for W is equal to the 7 points for W is equal to 1, these 5 points for W is equal to 2, these 3 points for W is equal to 3, and this just 1 point where 4 comma 4 may the minimum is 4. So just 1 point out of 16 total points where W is equal to 4. So this is the distribution of a function of two random variables x and y defined as such. Remember, the experiment was throwing a 4-sided fair die twice, or throwing 2 fair 4-sided dice. So this is how we generate and write the distributions of functions of two random variables. I'll give you a homework here. You have to carefully solve that. I'll simply note it down for you. So a homework now. Suppose that if x is the number of outgoing calls and y is the number of outgoing local calls and y is the number of outgoing long distance calls, from a certain phone exchange, the giant PMF of X and Y is given as such. So this is the giant distribution piece of X comma Y of X comma Y, and here you have X values, which is say 0, 1, 2, 3 and 4, and you have the values of Y, which is simply 0, 1 and 2 with this much probability is 0.23, 0.23, 0.11, 0.04, 0.01, 0.11, 0.11, 0.05, 0.02, 0.01, and then 0.03, 0.03, 0.01, 0.01 and 0. You need to find the probability of exactly 2 outgoing local calls and 2 outgoing long distance calls. So you need to simply find all these probabilities. This is part A. Part B, you find the probability of no outgoing local calls. So this is not that challenging, but you'll have to think, especially in one of these two subparts of the problem. But you'll have a good understanding of what we mean by the giant distribution and how we can find the probabilities of interest if we have the total giant distribution available to us. Students, we have now covered the basics of giant distributions. Now is the time to move on to discuss higher order statistics, and higher order statistics means in this particular course just two higher moments and the associated concepts, the expectation and then the variance. So we'll first cover the concept of expectation here. If you can understand these concepts, the remaining lectures in this particular chapter will become easy for you. So the next topic here is expectations. You already know that we can find the expectation of any random variable n by simply summing up along all the values of n, multiplying the value with the probability of the same value. Please note this. To find the expectation of a random variable n, you take one of its values, multiply this value with the probability of the same value, and then you do it for all the values of n, all such projects, and then these products are ultimately summed up, and this will give you the expectation of a single random variable n. We can extend this concept to more than one random variable. So the expected value of, say, random variable w, which is obtained by applying some functional form on x and y, is denoted as this E of w, and this is nothing but sum on x, all possibilities, sum on y, the functional form applied on x and y, times the giant PMF. You see here there are just three entities. To find the expectation, you have the sum operator, you have the random variable, its values one by one, and then the PMF of the random variable. So just three entities: the summation, the variable, and its distribution. And in this setup, it gives you the expectation. Same goes here: the summation, the functional form, this is nothing but w, and then the distribution, the PMF, the probability distribution of w. So we'll use this, but before that I'll give you one special function of two random variables that will be used later on in your higher subjects, higher courses like communication systems and maybe digital signal processing. So I'll discuss an important theorem here, and that says for any two random variables x and y, the expectation of the sum is basically equal to the sum of the individual expectations. Remember, this is always true for x and y, for either discrete or continuous random variables. But there is a big understanding, the big concept that needs to be explained here. You see, to find the expectation of the sum, if you do not know this theorem, just imagine how will you, if somebody gives you that you have some function of x and y which is nothing but x plus y, and so you say this is your w, then how can you find the expectation of this? The basic way is using this particular theorem, which means the expectation of w, or in other words the expectation of x plus y, will be summation on x, summation on y, x plus y times p sub x comma y of x comma y. You'll have to go to this if you do not know this particular theorem. If you do not know this theorem and then you are told to find the expectation of this function of two random variables x plus y, a special functional form, you will go through this path. You take the functional form, you multiply it with the corresponding giant PMF, and then you'll get it. But if you know this theorem, this is so easy to find this. You see, to find the expectation of x plus y, which is a function of two random variables, you do not even need to utilize the giant distribution, because you see from here you simply need the distribution of x to find the expectation. How? The expectation of x is summation on all x, x times the PMF. And for y, you can do the same. The expectation of y is summation on y, y times p sub y of y. So you see, to find the expectation of the sum, you do not even need to utilize this giant PMF. You simply find the individual expectation of x, for which you do not need the giant distribution, you simply need the marginal distribution of x, and then you find the expectation of y, for which you do not need the giant distribution, you simply need the individual distribution of y, and then you simply sum them up to get the total expectation of the sum. This is a very, very important theorem, because this is what you will be using hopefully in courses on communication systems and DSP at the appropriate level. So please keep this theorem in mind. Expectation is the average value, or the expected value, or the mean. All these concepts, or all these names are for the same thing, expectation or the averages. We'll move on. The expectation is done. You can easily find now the expectation of sum of two random variables x in this particular form, x plus y, by simply summing up the individual expectations. This is true for every case, whether it is discrete random variables or whether it is continuous random variables. By the way, we'll start handling continuous random variables from chapter number 4 onwards. One more concept. We have discussed the first order statistics, which is the expectation. Now we'll move on to discuss the higher order. We know when we have a PMF, when we have a random variable, we can have a PMF, and when we can have a PMF, we can have the expectation and variance. But here we are handling a special case, and that is the sum of two random variables in the form x plus y. So this is a special function of two random variables in the form x plus y, and we noted how we can find the expectation of the sum, and in just a few minutes ago we noted that the expectation of the sum is equal to the sum of individual expectations. This is one point. What about variance of the sum? This is now the question at hand, and I'll explain how we can find the variance of the sum. This has got some special significance. So I say through a theorem that if we have two discrete random variables, the variance of the sum is equal to the variance of the first random variable plus the variance of the second random variable plus 2 times expectation of x minus the mean of this variable multiplied with y minus the mean of this variable. And then this part has some special significance which I'll later explain. But first let's see why we were able to write this variance of x plus y in this particular form. This is the formula, but how we arrived at this formula, let me give you a small proof for that. Variance of x plus y by formula should be what? The expectation of, the variance of a random variable is always, say variance of x, this is always the expectation of x minus the mean whole square. So if you utilize the same concept here, your random variable is x plus y now, another form of a function. So this is x plus y, and then you subtract. You take the variable to find the variance of a random variable. You take the variable, and then you you subtract the expectation of that, and then you square it, and then you find the and then you find the expectation again. So now this is our assumingly one random variable, call it w, no matter. So x plus y minus the mean of this whole thing. So you denote it as mu sub x plus y, and then you square it, and then you find the expectation. You will get the variance of x plus y. But how can we turn it ultimately into this shape? We'll see. So this is the expectation of x plus y minus, this can be written as mu x plus mu y, and then whole square. Why we could write it as such? We just noted a few minutes back that the sum of the two random variables, their expectation is equal to the sum of the individual expectations. So this the sum of the mean of the sum is basically the sum of individual means. So this and this have the same meaning. So now simply we can write it as, we do not break the operator here, expectation operator. We can simply write, open this a minus b formula. It is x plus y whole square plus a square plus b square, which is mu x plus mu y whole square minus 2 times ab, which is x plus y times mu x plus mu y, and then the bracket. So now we can write it as the expectation of, open this, x square plus y square plus 2xy plus, now open this, mu x square plus mu y square plus 2 mu x mu y, and now open this as well. So I can write it as minus 2 mu x mu y, sorry, this is minus 2 x mu x minus 2 x mu y minus 2 y mu x minus 2 y mu y. And now combine the terms. So you get expectation of x minus mu x whole square plus y minus mu y whole square, which means you pick this, x square plus mu x square minus 2x mu x, this term. So these three terms combined gives you x minus mu x whole square, and similarly y minus mu y whole square, and the rest is basically 2 times x minus mu x times y minus mu y. You can open it and verify if I was wrong or right. So now we can simply distribute the expectation operator. So I can write it as expectation of x minus mu x whole square plus expectation of y minus mu y whole square plus 2 times expectation of this term, which is x minus mu x times y minus mu y. So now what is this? Is it not variance of x as per the basic formula? Variance of x is always x minus the mean of x squared and then expectation. Now variance of x is equal to x minus its mean squared and then expectation. So you see here it is x minus the mean of x whole squared and then expectation. All this can be written as variance of x. Similarly, this part is variance of y, and this part is 2 times expectation of all this, but I write it as covariance of x and y. And then I'll see how we can simplify this as well. As yet, we have been able to prove that we can write the variance of the sum of two random variables in this particular form. The sum of two random variables x and y is simply the individual variances, the sum of individual variances plus 2 times the covariance term. So this is an extra term that is there. This term can vanish in a particular case. I'll tell you about that case when time comes. But at the moment, we'll see how we can write this in a simpler form, which means the covariance of x and y. So you see this is an entangled kind of term. No matter what you do, you cannot separate x from y, and that is why they are called covariance. The word co, the indicator co, is important here. They vary with respect to each other, and this term can vanish in a particular case, but that case I'll discuss when I reach a particular topic. Till yet, just remember this formula. The variance of x plus y is always equal to variance of x plus variance of y plus 2 times covariance of x and y. Remember, this is not x plus y, this is covariance of x and y, the giantly varying. And this covariance can be written as the expectation of x minus its mean times y minus its mean. We'll move on and see how we can further simplify this particular term in the next part. So students, we have developed that covariance of x and y is nothing but the expectation of x minus its mean times y minus its mean. How can we write it in an even simpler way? Let's see. So I write it as expectation of, just open the product now, xy minus x mu y minus y mu x plus mu x mu y. And now distribute the expectation. So I can write it as the expectation of xy minus the expectation of x mu y minus the expectation of y mu x plus the expectation of mu x mu y. And so this term stays the same as yet, minus, look at this particular term, mu x is a constant, it is a mean, so it can always be taken out of the expectation operator, and the rest is basically, so you see mu y taken out and the rest is the expectation of x. And similarly here, mu x taken out and the rest is expectation of y. This all is constant, so the expectation of a constant is the same constant, so I can write it as mu x mu y. The expectation operator simply vanishes. So now I write it as expectation of xy minus, this is nothing but mu x, so I write it as mu x mu y. This is mu x and then mu y. And similarly here, minus mu x mu y and plus this is mu x mu y. So one term is cancelled with this one. So what we are left with is the expectation of xy minus the expectation of x times expectation of y. So now always remember that the covariance of two random variables is basically it can be taken as mean of product minus product of mean. You see, this is mean of this product minus the product of the two individual means. So the covariance will always be equal to mean of product minus product of means. If you recall, variance was mean of square minus square of the means. If you recall, just as a memory aid, mean of square minus square of the mean. This was for one random variable. When it comes to two random variables, you call it covariance, and it ultimately reaches at the stage where we can simply remember it as mean of product minus product of means. So the variance is mean of square minus square of the means, and covariance is mean of product minus product of the means. So now we will conclude that the covariance of random variables x and y is basically the mean of product minus product of the individual means. Do not forget this. Do not forget this, please. And by the way, I told you that covariance is basically the giant variance of two random variables. Just imagine if x is equal to y. Just imagine if x is equal to y, then it means that both the random variables are the same. So you can write x equal to y, and if you write x equal to y, covariance turns to be variance. It should turn to be a variance. Let's see how we can write this. So I say that if x is equal to y, then it effectively means that we have got just one random variable. And in that particular case, what about covariance of x and y? You know it is expectation of xy minus expectation of x times expectation of y, but we said that x is equal to y, which means this term becomes expectation of x into x, which is x square, minus take y as x, so it is again expectation of x times expectation of x. So this becomes expectation of x square minus expectation square of x. Is it not variance? So you see, when you have x is equal to y, covariance turns out to be variance. And this part in the expression of covariance is called correlation. You denote it as gamma sub x comma y. It will have some significance, but this will be taught to you guys in a course on signal and system, and then in DSP. At the moment we will not put more time on these things. Just remember that this product is basically the correlation gamma xy. You also call it correlation. I'll take an example and then we'll wind up today's lecture. So students, we take an example which we have already taken. So a quick look on that. You have a giant distribution p sub x comma y of x comma y, and then you have values of y and you have values of x. X is equal to 0, x is equal to 1, x is equal to 2 here, y is equal to 0, y is equal to 1, and y is equal to 2 here. The distributions are 0.01, 0, 0, 0.09, 0.09, 0, 0, 0, 0.81. And from here you can easily find the marginal distribution of x, sorry, of y will basically be the sum of the giant distribution points along x-axis. So you sum this, you get 0.1, you sum this, you get 0.09, you sum this, you get 0.81, and here p sub x of x will give you the distribution of x when you sum the giant distribution points along y. You see, to find the distribution of x, you sum along y. So all this becomes 0.01, all this becomes 0.18, and all this becomes 0.81. So you have now obtained the two individual distributions. The example says that we need to find the correlation between x and y and the covariance of x and y. You know that the covariance is basically mean of the product minus product of the means. So you need to find this thing and this thing. So first we find the correlation of x and y, and you know this is nothing but the expectation of the product, as we did in a few lectures back. You see here, covariance of x and y ultimately reaches to two terms. Mean of product, you call it correlation as well, and the second part is product of the individual means. So now we are required to find for this particular example, we are required to find the correlation and covariance. So within this covariance term we have correlation term. So first we find the correlation term, and then we'll use this and this to find the covariance. So what is the correlation? It is the expectation of the product. So this is nothing but summation on x, and x is running from 0 to 2, and another summation on y running from 0 to 2, the product times the giant distribution. Please do not forget that the expectation of anything, any random variable, is summation on all the possible values of the same random variable, the value of that random variable, one of the values of random variable, times the probability of that value. Okay, and you repeat these this for all the values of x, and then you sum all those product to get the expectation. So here it is two random variables, so we'll have x times y, the function within, and then and since it's a function of two random variables, so you will use the giant distribution, which is by the way given here. So it's not a big deal, we can easily find this. Okay, you do the products, you run x from 0 to 2, you run y from 0 to 2. So this is like two embedded loops. You take x is equal to 0, and then you run y from 0 to 2 using this formula. Then you take x is equal to 1, and then you run from y is equal to 0 to 2 using this formula, and then x is equal to 2, and then you run it again, and then all these are put together will give you the correlation of the random variable x and y. So here the product is so easy. The only non-zero products are x is equal to 1, y is equal to 1 times its probability. X is equal to 1, y is equal to 1 times its probability 0.09 plus x is equal to 2, y is equal to 2 times its probability, which is 0.81. All the other products are 0, either because of the value of the random variable is 0 or the probability point in the giant distribution is 0. You can, for example, take any other product. If you take, say, this product, x is equal to 2, y is equal to 1, so it is 2 into 1 times probability 0, so that the product ultimately will be 0. If you take x is equal to 0, no matter what the probability or the value of y is, because of the 0, this product will go to 0, and so on. So the only non-zero products are just these two entries, x1 y1 and x2 y2. So this ultimately reaches 3.33. So this is the correlation. Now we'll find part B, which is covariance of x and y. You sometimes write it as sigma sub x comma y. Okay, and this is basically gamma x comma y minus mu x mu y. Please don't forget this, it should not confuse you. Covariance is basically the mean of the product. We call it correlation. So this is the correlation part, and then the other term is the expectation of the product of the individual expectation, which is mu x mu y, mu x mu y. We already know this. This has been found here. So we need to simply find this and then subtract the product from this, and we will get the covariance value. How to find mu x mu y? It is so simple. You have got the individual distribution of x, you have got the individual distribution of y, or the marginal distribution of x and marginal distribution of y. From there you can easily find their corresponding means. So expectation of x, or you call it mean of x, can be calculated as summation x is equal to 0 to 2 x times p sub x of x. And so it is, you see, the value of x times its probability plus the next value times its probability plus the next value times its probability. So 0 into this goes to 0, 1 into this is 0.18, and 2 into 0.81 is something. So we have 1 into 0.18 plus 2 into 0.81, and we'll have 1.80 as the expectation of x, or mu of x. Similarly, expectation of y, or mu sub y, is summation y is equal to 0 to 2 y times p sub y of y, and that will be equal to 1 times 0.09 plus 2 times 0.81, and that will reach 1.71. So now the covariance here becomes 3.33, the correlation value, times the product of these two individual expectations, minus 1.8 into 1.71. So we'll ultimately reach at 0.252. So this is the covariance. We'll not move further. We'll stop the lecture here, and I'll give you a quick repeater. Just give me a minute so that I could arrange my slides. So students, let me give you a quick repeater. We in the first part of the lecture, in the previous lecture, we discussed the concept of giant distributions of probability distribution of PMF of two random variables, and then from there we discussed the concept of how to find the individual distribution of the two random variable, and then I gave you a quick hint that the sum of all the probability distributions is always equal to 1, no matter what their dimension is. Whether it is two dimensional, the sum is 1. Whether it is one dimensional, the total sum is always equal to 1. In today's lecture, we started off with the concept of functions of two random variables and did some small example. And again we see that whether it is a function of two random variables or a single random variable, the total probability sum in a distribution is always equal to 1. I gave you a quick homework problem as well. I'll strongly recommend that you do solve this problem. It will further clarify the concept of giant distributions in your mind. Then we move on and said that since we have giant PMF as a proper PMF, so we should have higher statistics, and for higher statistics in this particular course we simply mean the expectations and the variances. The expectation can always be written as this, which is when you break the expectation operator, you get three entities. One is the summations, the other is the functional form within, and the third is the distribution. For a single random variable, the same concept applies, but on one random variable only. And then we discuss a special case of a function of two random variables, and that is the sum of two random variables. And we wrote that the expectation of the sum is always equal to the sum of individual expectations. Okay, and this formula also gives you a clue on if you have the giant distribution available, you do not even need to utilize that giant distribution to calculate the expectation of the sum. You simply can sum the individual expectations, and this will give you the expectation of the sum of the two random variables as well. This was the first statistics, the expectations. The next is variance of the sum. So this is variance concept for two random variables, for the sum of two random variables. You know, for a single random variable, the variance is given as the value minus the random variable minus its mean whole squared, and then the expectation taken. For variance of x plus y, I claimed that we can write it as variance of x plus variance of y plus 2 times this term, and then we proved here how we can write this variance as all this. So we moved on here and ultimately reached this stage where we could write it as variance of x plus variance of y plus 2 times the same term as here. And then I claim that I call it as covariance of x and y, because no matter what you do, you cannot separate the terms x from y, except a special case which I will not discuss at the moment. But there is a quicker way of finding this term. Instead of finding this expectation, you can find the same thing in a simplified manner. How we can do that? So we basically developed a short method of finding this covariance. How? You see, covariance can be written as this, and then we moved on. Ultimately we reached this, and we have now two terms. One is the mean of the product, and the second is product of the means. If you recall, for the variance of a single random variable, we had this concept of mean of square minus square of the mean. For the covariance, we have mean of product minus product of the means. And then I said as this first term, the mean of the product, is also called correlation. Its physical significance will be explained in a course on signals and systems. At the moment, we just see how we can calculate that. So now this is the formula for the covariance. Then I also said that if we have just one random variable, which means even for the two random variables, if they are the same, then the variance should logically be, the covariance should logically turn out to be variance, and we have established how it can be done. So the covariance, if x is equal to y, the covariance ultimately turns out to be the variance. Then we did an example where we were to find the correlation and covariance of random variables x and y using this data, which is already given as an example. And from the giant distribution, we can find the individual or marginal distributions of y and x. The correlation is simply this, and covariance is this. Please do solve the end chapter problems, the relevant end chapter problems in parallel to the lectures. Once the lecture is over, you just listen and attend the lecture, and then try to solve some relevant end chapter problems. Thank you very much. In the next lecture, we'll see how we can understand, we'll discuss the conditioning, we'll discuss conditioning a giant PMF by an event. So the next lecture, inshallah, we will be discussing the conditional probability concepts in cases of giant distributions. For now, it's over. Thank you very much, and good luck. Stay safe.